Okay, good morning, everyone. We're going to get started with our class now. Okay, so so first of all, welcome back to the class. We missed a few lectures because of this lockdown situation. So I hope you guys are all doing okay with the lockdown, right? So I'm stuck in my apartment also, and obviously it's not a fun experience being locked into your apartment. I think if you're having some sort of problems dealing with the lockdown, then the best I can suggest is to maybe try to find something interesting to do. Okay, just find something you like to do, and then just focus on that, and then sort of not think about this other situation. Okay, that's what I'm trying to do, and so maybe that can help a bit. All right, so I think it's also good that we're resuming classes so that we're at least getting back to some sort of normal life. Okay. All right, so then let's do today's lecture. So today we're going to talk about this this topic which is called extending tractability. Okay, and so what we mean by this is that we study these NP-complete problems, and we said that these problems are in the worst case we don't have efficient solutions for them. Okay, in the worst case, usually we have to rely on some exponential time algorithm to solve these problems. Okay, and I don't want to give the impression that once you encounter one of these NP-complete problems, you should completely give up. Okay, because the first time you see this result about sort of needing to use exponential time for these algorithms, you might just say that, okay, as soon as I hit one of these NP-complete problems, I'm just going to sort of stop looking at this problem because it's impossible to solve. Okay, well that's not the right way to think about this. Okay, because in fact, in practice, when you do computer science, you're going to see these NP-complete problems come up in real life all the time. Okay, so you can't just give up at that point. You have to find some way to try to do the best you can with these problems. Okay. And so people have found different ways of dealing with these NP-complete problems in practice. Okay, so for example, here on this over here, we listed some methods that people have tried to use to deal with these very difficult problems. One method is to not try to solve the problem optimally. Okay, so what we proved when we talked about these NP-complete results is that if you try to find an optimal solution for some problems, it might be very hard. Okay, but you can give up on that goal, and you can just say that I want to find an approximately optimal solution. Okay, so maybe I don't need 100% optimal. I'm okay with 90% optimal, or even 50% optimal, or something like that. Okay, and in certain cases, once you give up this requirement of finding the best possible solution, then it is possible to find approximately optimal solutions. And so, in fact, these types of algorithms are called approximation algorithms. And we're going to spend some time towards the end of this course talking about different types of approximation algorithms. Okay, so you might have a problem which is NP-complete to solve optimally, but it is polynomial time solvable in if you go for approximations. Okay, so that's one method. Another method is that you can just give up this goal of trying to solve the problem in polynomial time. Okay, and so you can just settle for an exponential time algorithm. However, it turns out that sometimes, even if you have an exponential time algorithm, it is still feasible to run these algorithms on practical instances of the problem. Okay, depending on how your exponential algorithm looks. So what we're going to see today are some algorithms where we only have exponential time solutions, but the exponential part is with respect to a parameter which is small. Okay, so you might have a very large problem, like you have a graph with 1,000 nodes. Okay, but with respect to this graph, we can sometimes find these parameters, which I'll show you examples of these later. Okay, and these parameters might be very small in practice. Like maybe for 1,000 nodes, your parameter is only 10. Okay, and so now if you have an exponential time algorithm which is exponential in these small parameters, okay, then in practice it's still feasible to run these algorithms. Of course, in the worst case, your parameters might also be very large. Okay, so in that case, you still can't run this exponential time algorithm. But but sometimes for many practical instances, you have small values of these parameters, and so then you can run your exponential time algorithm. Okay. And the final approach that people take to solving these NP-complete problems is to not try to solve all instances of these problems, but just try to focus on particular instances of the problems which might be easier to solve. Okay, so for example, we saw that in the worst case, the Hamiltonian path problem is hard to solve. Okay, if I give you an arbitrary graph and I ask you to find a Hamiltonian cycle, then this is NP hard to do. Okay. However, there are certain graphs where it's very easy to find Hamiltonian cycles. Right? So for example, if I just give you a cycle graph, okay, then that by itself is a Hamiltonian cycle. Okay, and there are other examples of graphs where it's easy to find the solution if you only focus on certain types of graphs and not all arbitrary types of graphs. Okay, and so today we're also going to see an example of problems where we're going to focus on specific types, specific instances of the problem, and that's going to make the problem easier to solve. Okay, yeah, so this is basically what we mean by coping with, or by extending tractability, which is that if you try to solve the problem in full generality, like you want optimal solutions in polynomial time on arbitrary instances, then we don't have a way of doing that. Okay. However, if you sacrifice one of these requirements, then we can find efficient algorithms. All right, so let's get started with this. Okay, so we're going to look at several problems today. Right. And I might not have time to go through all of the problems because for some reason these lectures are shorter than usual. Okay, so so I might have to skip some of the problems, but then you can look at these notes later. Okay, and then it should be pretty understandable. Okay, so so the first problem we're going to look at is this problem called vertex cover. Okay, so the situation is that you're given this graph. Okay. And what you need to do is to select a subset of the vertices. And the subset of vertices needs to cover all of the edges. Okay, so for example, here in this graph, let's select these blue vertices over here. Okay, now these blue vertices are going to cover all of the edges in the sense that, for example, if you take this edge, okay, this is being covered by this 6th vertex because, the 6th vertex touches this edge. Okay, so therefore it covers this edge from 1 to 6. Okay. Likewise, the 6th vertex also covers this edge. Okay. The 7th vertex covers, let's say, this edge and that edge and all of these other edges which are adjacent to 7. Okay. Yeah. So for each vertex, it covers all of the edges that it touches. And now, let me just erase this here. Okay, and now what we're trying to do is to, we want to cover all of the edges in this graph. Okay. And furthermore, we want to use the fewest number of vertices possible to do this. So for example, if you use all the vertices, then of course you're going to cover all of the edges. Okay. But it turns out that in this graph, you can use only 4 vertices, and you can still cover all of the edges. Okay, so let me just talk about like one possible application for this problem. Okay, so one application would be that if you think of these edges as so suppose you're in like a museum, okay, and these edges are like hallways, okay, and sort of in these hallways you have all these like expensive paintings, okay, so you want to make sure that nobody like touches or steals your paintings or something. So therefore you're going to put security guards at these nodes. Okay, so the nodes are like intersections of the hallways. And if you put like if you put a security guard over here, he can watch this entire hallway and he can make sure that nobody steals any of the paintings in this hallway. Okay, and also this hallway and all of the hallways that this node touches. Okay, right, so yeah, so our goal is to make sure that all of the hallways are covered by some security guard. Okay, like the 7 guy, he's going to cover, all of these hallways that he can see. All right, and of course, we want to hire as few security guards as possible, and so therefore we want to have a minimum vertex cover. Okay, so that's sort of like one type of situation where you might want a vertex cover. right? So yeah, so this is actually a pretty widely used problem, and also it's NP complete. Okay, so therefore, if I give you a general graph, right, then we're not able to find a minimum vertex cover in polynomial time. However, it turns out that for many graphs, it's possible to cover the graph using a small number of vertices. Okay, so for example, for this graph, we only need 4 vertices to cover all of the edges. Okay, so then the question is that what if I give you a graph and I just want to cover it with a small number of vertices, and see if this is possible to do? Okay, because maybe if I select k here, right, the number of vertices to be too small, then it's not possible to cover all the vertices. Okay, but maybe even for small k, it is possible to cover all the vertices. Okay, so suppose it is possible to cover all the vertices using a small number of cover all the edges using a small number of vertices. Okay, then can we solve this problem in some sort of more efficient manner? Okay, so one thing is that if you say k is small, then you can maybe try a brute force approach. Okay? So for example, if I say that k is 1, so that means I'm trying to cover all of the vertices, all of the edges. Sorry, I keep saying vertices, but I'm trying to cover all of the edges using 1 vertex. Okay, well, I can do that I can try to do that in polynomial time, because all I need to do is I'm just going to go through all of the vertices and check whether any of them can cover all of the edges. Okay, and that's just going to take me like order e time, where e is the number of edges. Okay, so that's a polynomial time algorithm. But now if k is larger, okay, then what I might try to do is I'm going to look at all subsets of k vertices, and I'm going to see whether this subset can cover all of the edges. Okay. So now how much time is this going to take? Well, first of all, if I do this algorithm, then first I need to try all the subsets. Okay, so the number of subsets is basically n choose k, where n is the number of nodes and k is the number of vertices I'm going to use to cover all the edges. Okay, so n choose k basically is exponential in both n. Well, it's order of n to the kth power. Okay. And so there are this number of subsets I need to consider. And for each subset, I need to check whether the subset can cover all of the edges. Okay, and that's basically going to take me order n times k time. Okay, because for each of these k vertices, I need to check all its neighbors, and it can have up to n neighbors. So therefore, the total amount of time for this pure brute force algorithm is going to be the product of these two things, which is going to be this thing over here. Okay. Now this function, okay, even if we try to run this brute force algorithm for reasonably small values of k, right? We're going to see that this is still not feasible, because for example, if you have a graph with 1,000 nodes and you try to cover it with 10 nodes, okay, well, this brute force algorithm is going to take something like 10 to the 34th power to run, okay, and that's completely infeasible. Okay, so the pure brute force approach is not going to work. Okay. However, we can still try to go for some sort of exponential time algorithm, except for it's a better exponential time algorithm. Okay, and what I mean by that is, suppose we try to find an algorithm where it has exponential running time, but instead of being n to the k, right? So here you have n to the k exponential running time. Okay. So suppose you can find an algorithm instead that has 2 to the k exponential running time, okay, times some polynomial stuff. Okay. Then this is still an exponential time algorithm, but if your k is not too large, this is actually a feasible algorithm. Okay, so for example, if your n is 1,000 and k is 10, then if we can find an algorithm which has running time basically 2 to the k power, then this only takes 10 million steps. And this is quite feasible. Okay, so that's what we're going to try to do. Okay, we're still going to look for an exponential time algorithm, except for it's a better exponential time algorithm. It's not an n to the k time algorithm. It's like a constant to the k time algorithm. Okay, so let's see how we can do this. All right, so Yeah, so the main observation is, so the main way we're going to do this is to make use of this observation right here, okay? So, so the claim here is saying that, if you have a graph G, okay, then suppose it's, you can cover this, you can cover all of the edges using at most k vertices, okay? Then, if you consider these other two graphs, okay, G minus U and G minus V, so I'll show you what these are later, okay? But if you consider these two other graphs, then at least one of them can be covered using at most k minus 1 vertices. Okay, so this is the key property we're going to use. Okay, we're going to start with a large graph, and we assume it can be covered using k vertices. Okay, and that's going to imply that one of these smaller graphs, G minus U or G minus V, okay, that can be covered using at most k minus 1 vertices. Okay, so this gives us some sort of induction that we can do. Okay, then we can take these two smaller graphs, G minus U and G minus V, and then try to cover them using, and then we can sort of reuse this claim, and then we can get an even smaller graph, which can be covered using like k minus 2 vertices. Okay, so then we just sort of keep going that way. Okay, so that's basically how we're going to make use of this claim. All right, now of course before that I need to show you what this G minus U and G minus V is. Okay, so let me just give you an example of this. So so suppose you have a graph which is like let's say it looks like this. Okay, and let's say that this is node U over here. Ugh, why can't I write on this? Okay, so this is node U, and let me make a node V also. Okay, oh jeez. All right, this is a node V over here. Oh, what's wrong with this computer? Right, I'm sorry, there's something wrong with this computer. Okay, all right, so I guess I can't touch my screen while I try to write. All right, okay, so this is gonna be G over here, okay? Now, G minus U, okay, G minus U. So I'm trying to not touch my screen, so my writing is sort of messed up, okay? G minus U is that we're just gonna take out this node U and all of the edges adjacent to U. Okay, so therefore, if you take out edge U and all its adjacent edges, oh, geez, what is happening? Okay, all right, all right. So I don't know why this is. Oh, geez. Yeah, I'm sorry about this. My computer is having some problems. All right, then let me try to write below this point. Okay, so. So if you take out node U, so all right, so we're, oh my goodness, all right, yeah, guys, I'm sorry about this. All right, so this is going to be G minus U over here. Okay, so we're going to take out node U, right? We're going to take this out and all of its edges. Okay, so therefore what it's going to look like is, what is this going to look like? I guess it's going to look like this. Okay, so you have node V over here, and then you used to have a node U, right, with 4 edges, but now we take out all those 4 edges. Okay, so this here is going to be G minus U. Okay. Oh, this is really bad. All right, and then if you want to look at G minus V, okay, so what you do there is you take out V and all of its adjacent edges. Okay, so therefore what you're going to have is just this little diamond shape over here. Okay, right, so this is going to be G minus V. All right, so those are, yeah, so this is how you take, so when I say G minus a node, I mean that you take out the node and all its adjacent edges. Okay, and again, the claim is that, oh, Jesus. All right, sorry. Okay. Yeah. And the claim is that, yeah, if you can cover the whole graph using k vertices, then you can cover at least one of these graphs using k minus 1 vertices. Okay. And the reason for this is actually quite simple. Okay. So, so this is an if and only if. So suppose, first of all, that you can cover the graph using k vertices. Okay, then let's pick any edge UV here. Okay, then because we have a vertex cover, then either V or U has to be in the vertex cover. Right, we have to select either node U or V. Otherwise, there's no way to cover this edge between u and v. Okay, the only way to cover that edge is either to select u or v. Okay. So now assume that we selected node u to be in the vertex cover. Okay. So now once you take out node u, right? So you go from this g graph over here to this g minus u, right? So you took out one node from your cover, right? And initially you covered the entire graph using k nodes, right? One of which was u. And now after you take u out, you can still cover the rest of the graph using k minus 1 nodes. Okay. Yeah. Right. So this. So this shows that this shows the one direction where So this shows this direction over here, and then for this other direction, suppose you can actually cover this g minus u graph using k minus 1 nodes. Okay. Well, then if you just add back this u node, right, then you can cover this entire graph g using k nodes. Right, because now you can cover all of these edges which were adjacent to u using this one extra node. Okay, so therefore we have this claim. Okay, now the next claim is that suppose you have a graph with a vertex cover size k. Okay, then the claim is that at most this graph has k times m minus 1 edges. Okay. And the reason is because if you have a vertex cover of size k, right, then if you select these nodes, right, in the vertex cover, then they cover all of the edges. Okay. However, each node in the vertex cover can cover at most n minus 1 edges. Right. Each node is adjacent to at most m minus 1 other. Each node is adjacent to at most n minus 1 edges. So each of these k nodes can cover at most n minus 1 edges. And since you have at most k of these nodes, then in total you have at most k times n minus 1 edges. Okay, so therefore we have these two claims, right? And once we have these claims, then we can use these to develop an algorithm. Okay, so the algorithm is going to be that in order to cover a graph using k nodes, okay, well, first of all, we have these base cases where if the graph doesn't have any edges, right, then of course we can cover it using k nodes, because we're trying to cover all the edges, but it doesn't have any edges. Okay? Or if the graph has more than k times n edges, okay, then we know by this claim over here that it's not possible to cover this graph using k nodes. Okay? Because with k nodes, you can only cover this number of edges. Okay, so these are our two base cases. And next, we're going to make use of the first claim, and we're just going to pick any edge uv. Okay? And what we know is that if the overall graph can be covered using k nodes, then either g minus u or g minus v can be covered using k minus 1 nodes. Okay? So therefore, we're just going to try to cover g minus u with k minus 1 nodes, and also g minus v with k minus 1 nodes. And if either of these are successful, then we know that we can cover the whole graph with k nodes. And if both of these fail, okay, then we know that it's not possible to cover G using k nodes. So therefore, we're just going to call these two subroutines. We're going to recursively call our function, right? And then we're going to take the OR of these two results that we get. Okay, and this algorithm is correct simply by the first claim. Okay, right? Because we know by the first claim that if we can cover everything using k nodes, then we can cover one of these, at least one of these graphs using k minus 1 nodes. Okay, any questions about this algorithm? Okay, so now let's look at the running time for this algorithm. Okay, so basically, we have these two recursive calls over here for A and B. Okay, so if you look at the recursion tree that this is going to produce, what's going to happen is that so let's let t of nk be the running time when you have a graph with n nodes and you try to cover it with k nodes. Okay, so then t of nk is going to be, well, if k equals 0, then we just stop. Okay, if k equals 1, then you need to see whether you can cover this graph with a single vertex. Okay, and so that's going to take, so then you need to go through all of the edges. Yeah, so this is going to take c times n time. Okay. And in the more general case, right, we need to make 2 recursive calls, each of size k minus 1. Okay, so you see that here you have 2 recursive calls, each of size k minus 1. Okay. All right, and then after you make these 2 recursive calls, for each of these calls, you need to check whether your k edges that you select can actually cover all of the vertices. Okay, and so that's going to take c times kn amount of time. So therefore, you have this recurrence relation in terms of the running time. Okay. And if you solve this, you're going to see that in the end, your running time is going to be something like 2 to the k times something polynomial in k and n. Okay, so therefore we have now an algorithm which is only exponential in k and not in n. And because k is usually, we're only considering cases where k is small, then this, in certain cases is a reasonable algorithm. Okay, any questions about anything? Okay, all right, so then let's do the next problem, okay? So for the next problem, we're going to focus on some problems in trees. Okay, so the first problem we're going to look at is independent set. Okay, and so first of all, what is an independent set? Okay, so suppose you have a graph like this over here. So an independent set is again a subset of the vertices. Okay, but the requirement is that if you pick one vertex, okay, so suppose you pick this vertex, okay, then you cannot pick any of the neighbors of this vertex. Okay, so for example, this is not an independent set because these 2 guys are neighbors. Okay, on the other hand, you could pick something like, you can pick this node, right? And now you're not allowed to pick any of these nodes, but you can pick, let's say, this node, right? And you can also pick this node because these 2 nodes are not neighbors. Okay, and you can pick this node and so on. Okay, so we're trying to pick a subset of the nodes. And the only requirement is that none of the nodes can be neighbors of each other. Okay, so this is called an independent set. And now the problem we're trying to solve is that we're trying to find the largest independent set possible. Okay. Now, one sort of motivation for this problem is that suppose these nodes represent things that you're trying to do. Okay, and edges represent some sort of conflict between these tasks. Okay, so for example, one thing you might try to do is, let's say you want to watch a movie. Okay, so that's one of these nodes. Okay, so that's like a movie node. Okay, and then here you're trying to do some work. Okay, well, if you watch the movie, then you can't do work. Okay, so therefore there's a conflict between these 2 tasks. So so we put an edge between them, and that means that if you choose to watch a movie, you can't do work, and if you do work, you can't watch the movie. Okay, all right, and then maybe this task over here is like let's say sleep. Okay, so if you watch the movie, you also can't sleep. Okay. All right, so then this finding a maximum cardinality subset would correspond to like doing as many activities as possible which do not conflict with each other. Okay, so that's like one motivation for this problem. Okay, now in general, we can try to solve this maximum cardinality, this independent set problem on general graphs, and in that case, it's going to be NP complete to do. Okay, but now we're going to focus on a particular type of graph, which is trees. Okay, and we're going to see that it is possible to solve this algorithm efficiently when we only care about tree graphs. Okay, so so this algorithm is going to make use of this important fact, which is that no, sorry, this is not the fact of this. Yeah, so let's see. Yeah, so the algorithm is going to make use of this key fact. Okay, which is that if you look at a tree graph, and then you look at all the leaves. So the leaves are just these degree 1 nodes, right? So these are all leaves. Okay. So if you have more than degree 1, like this guy, right, or this guy, right, these are not leaves. Okay. So if you look at just the degree 1 nodes, okay, then there is so the key observation is that there is a maximum size independent set which contains a leaf. Okay, so for any leaf, okay, you can take any leaf, and it's guaranteed that there's a maximum size independent set which contains this leaf. Okay, so this is a key observation. Okay, all right. So first of all, let's try to prove this observation. Suppose you actually have a maximum size independent set. Okay, and then you took one of these leaves. Okay, now so your set is called S. Okay, so if V is already in S, then of course you're done. Okay, and otherwise, we're going to look at this node V over here and its neighbor U. Okay, so V only has one neighbor because V is a leaf, right? And so now if both V and U are not in the independent set, okay, then we can actually add V into the independent set. Right? Because if both of these guys are not in the independent set, then if you add V, you don't conflict with anything. Okay? So then you can add V and it's still independent, but then that's a contradiction because now S is not a maximum size independent set, right? Because we can add something to it and still be independent. And so the final possibility is that U is in the independent set. Okay? So here, suppose you already selected U to be in the set. Okay? But you did not select V to be in the set. Okay, and now what you can do is you can just take U out, okay, and you can replace it with V. Okay, so instead of having U be in the independent set, you're just going to put V in there and take U out, and this is still independent, right? Because V can only conflict with U, and we took out U. Okay, and this set, okay, this set has the same cardinality as your original S set, because you took one node out and you put one in. And so this means that there's always a maximum size independent set which contains V, the leaf. Okay, so now once we have this observation, we can just use it to develop an algorithm. Okay, so the algorithm is going to work like this. So what we're going to do is we're going to look for a leaf. Okay, and so you have a big graph, and then you just pick any leaf. Okay, and since by the previous claim or by this observation, right, we're guaranteed that this leaf is in the independence, is in some sort of maximum independent set. Okay, then we're just going to add this leaf to our S. This S is our final maximum size independent set. Okay, right, and now once you add V into the set, right, then V has some sort of neighbor U. Okay, then since you added V to the set, you cannot add set node U anymore. So therefore, you have to delete node U. Okay, and also node V. Okay, right. But once you delete node U, then that means that so if you delete node U, then that means that you're definitely not going to put U into your set S. Okay, so therefore, all of the neighbors of U do not conflict with U anymore. Okay, so therefore you can take out all of these edges from U to its neighbors because we're not going to put in U into S. And so U cannot cause conflicts with any of its neighbors. So therefore we can take out all of the edges between U and its neighbors. Okay, and then after that you just continue. Okay, you just continue doing the same thing where now you find another leaf, you add it to your set S, right? And then you take out the neighbor U of this new leaf, right? And you also take out all the neighbors of this new U node. Okay, so let's do an example of this. All right, so let's do an example. So suppose you start with an arbitrary leaf. Okay, so let's start with this one. Okay, all right, so we're going to put this into S, and then next we're going to take out its neighbor U. Okay, it only has one neighbor, and once you take out U, you take out all its adjacent edges. Okay. All right, so next we're going to find another leaf. So let's say this guy over here, right? And then you're going to take out its neighbor. And then you're going to take out, you know what? Let me, yeah, okay, you're going to take out its neighbor and all its adjacent edges. Okay, and then next we're going to find another another leaf over here. Oops. This is wrong. We're going to take out its neighbor, right? We're going to take out this guy, right? And then all its adjacent edges. And then we're going to, let's say, take this one, right? You take out this u and its adjacent edges, right? And now you can take this node, okay? And then finally over here, right, we can take this guy, right? We take out its neighbor and all their edges, and then we take this node, okay? All right, so that would be, so then in total, we have, let's say 1, 2, 3, 4, 5, 6, 7. Okay, so we have 7 nodes in our independent set. Okay, so that's how we run the algorithm. Any questions about this? Okay, so I'll just mention one more thing, which is that if you want to implement this efficiently, so you can definitely do this in polynomial time, just by sort of always looking for leaves and then taking out the neighbors and so on. Okay, but if you want to do this really efficiently in like linear time, okay, here n is the number of nodes. Okay, then one way to do this is to look at all of the nodes in post order. Okay, so post order basically means that if you so post order is a way to traverse this tree. So let me erase all this stuff over here. All right, my computer for some reason is very slow. Okay, so post order is a way that we can traverse the tree, and the order is that you're going to start at so you're going to root the tree in some way. Okay, so let's say that you pick this node as the root. Okay, and then we're going to start visiting all of the nodes. But whenever you encounter a node, you're first of all going to visit its entire subtree before you visit the node itself. Okay, so for example, if you start the root node, right, then instead of visiting the root node, you're first of all going to visit all of its subtrees. Okay, so for example, in the left subtree, you're going to visit this node. So this is going to be the very first node to be visited. Okay, and then you're going to go down into this subtree. But once you hit this node, you're not going to visit this node immediately. You're going to traverse. You're going to visit all the children of the. You're going to visit all of the children of this node. So which includes these two subtrees before you visit this guy. Okay, and so what that would do is, let me again erase this stuff. So what that would do is, instead of visiting this node, you're going to end up actually visiting this node second. Okay, and then you're going to visit this node third, and then this node fourth, and this is going to be number 5, and then 6, and then so on. Okay, so I think I'm doing that correctly. But anyways, so the idea is to visit a subtree, right? So instead of visiting this node directly, right, we visit its subtrees first. Okay, and if you do that, then you can look at this and you can see that it's actually possible to implement this algorithm over here in linear time. Okay. If you don't do it in post order, it's still going to be polynomial, basically, unless you do it in some very bad order. Okay, but basically any order that you do this algorithm in, it's going to be polynomial. But if you want like really fast running time, you should do it in post order. Okay, so that is okay, so that is the maximum independent set in trees. And now we're going to generalize this problem slightly. Okay, so now we're going to consider a still independent set, but now we're going to look for weighted independent sets. Okay, so what I mean by this is that suppose you have a graph. Okay, suppose you have a graph like this. So in the previous version, in the unweighted version, all we want to do is to maximize the number of nodes that you put into the independent set. Okay, so each node basically gives you a score of 1, and you want to get the maximum score. Okay, but now in the weighted version, we're going to give different nodes different scores. Okay, so in the unweighted version, if you look at this graph, the maximum independent set would have size 4. Okay, but in the weighted version, suppose you give these nodes weights. Okay, so suppose you make the middle node have a weight of 10. Okay, and then let's say you make all these other nodes have a weight of 1. Then in this case, you don't want to select these outside nodes anymore if you want to maximize the weight. Okay, so we still want to select an independent set, but the maximum weight one would be just to select the middle node, and then you get a weight of 10 for that. Okay, yeah, so we're just trying to select maximum independent sets. However, now all of the nodes have weights, and we want to maximize the total weight of the nodes that we select. Okay, so right? So this observation here is actually not that useful. So I'm not going to talk about this. Okay. So instead, I'm going to go directly to the way that we're going to solve this, which is that so we can't use this previous approach anymore. Okay. So this previous approach is basically like a greedy algorithm where you just look for these leaf nodes and you keep adding the leaf nodes. Okay. So once you have weights, then you can see, for example, in this case, right, that we can't just add the leaf nodes. Okay. So instead, we're going to go for a dynamic programming solution. So what we're going to do is we're going to take this tree and you're going to root the tree, okay, at some node, at an arbitrary node. Okay, so for example, let's pick this node to be the root. Okay, so the reason you want to pick roots is because once you have a root, then you can start talking about subtrees, right? So for example, the root subtree would be these two subtrees, right? And then also for any other node, right? For example, for this node, okay, it also, you can talk about its subtrees. Okay, so once you have a root, you basically set a direction for the tree, right? The tree grows out of the root. Okay, and once you have this direction set up, then you can talk about subtrees. Right? Subtrees grow farther and farther away from the root. Okay, so so the reason we need to talk about subtrees, okay, is because in our dynamic programming algorithm, we're going to define these two things. Okay, so what we're going to do is suppose you have a node over here. Okay? Then either you can add this node to your independent set or not add it. Okay, now in the first case, if you add this node to your independent set, then what you know is that you cannot add any of these children nodes of this guy. Sorry, I drew this incorrectly. Let me yeah. So if you add u to the independent set, okay, then you cannot add any of these children nodes. Okay, and if you don't add u, right, then you have a choice whether to add these children nodes. Okay, so if you don't add u, then maybe you want to add this guy, but you don't want to add this one, and you do want to add this one. Okay, so you have a choice. If you don't add u, then you have a choice for each of the children whether to add it or not. But if you do add u, then you don't have a choice. You just cannot add any of the children. Okay. All right. So now we're going to define these two quantities: opt in of u and opt out of u. Okay. So opt in of u is, suppose you look at the subtree rooted at u, and suppose you choose to include u. Okay. That's why we say it's opt in, right? Because we choose to include u. Now, if you choose to include u, then what is the maximum weight independent set in this subtree if you choose to include u? Okay, that's what this opt-in of u means. Okay, we're going to look at the subtree rooted at u, and we're going to include u. And then we're going to look at what is the maximum weight independent set given that we have u. Okay. Now the opposite of that is opt out of u. Okay. So this means that we're still going to look at this the subtree rooted at u, but we're not going to include u. Okay. And then after we make that choice, conditioned on not including u, we're going to look at the maximum weight subtree, maximum weight independent set in this subtree. Okay. So in both cases, we're going to focus on this subtree rooted at u. And in the first case, we're going to include u and then look for the best solution. And then in the second case, we're going to choose not to include u and look for the best solution. Okay, so that's how we're going to define these things. And now we have these dynamic programming relationships. Okay. So the first one, okay. So the first one is where you do choose to include u. Okay. Now, if you include u, right, so if we include u, then automatically we get the weight from u as part of our solution. Okay, and then furthermore, we know that once you include u, you cannot include its children. Okay, so therefore, for all of the children of u, right, none of these children can be included. Okay, right. So for example, for this w here, okay, this corresponds to so now we're going to look at the subtree rooted at w, and we know that in this subtree we cannot include w. Okay, we can include some of the other nodes in the subtree. So for example, this node, we can include that one. but we cannot include W. Okay, and then same thing for all these other subtrees. We cannot include the roots of these subtrees. Okay, so that's the first relationship, okay, for opt-in. And then for opt-out, sorry, let me just erase this again. Sorry, it's very slow. I don't know why this is happening, because I don't have any other processes running. Okay, all right. Now for the other relationship, okay, where you we're again going to focus on the subtree, but then you do not include U. Okay. Now you have a choice for each of these other subtrees. Okay, for this subtree, and for this subtree. You have a choice whether to include the roots of these subtrees. Right? You can choose whether to include V and W and X. Okay. And how do you make that choice? Well, just whichever one is better, okay? So for each of these subtrees, you're going to look at whether it's better to include this root or not include this root, okay? So, so for each of these subtrees, you're going to look at whether it's better to include the root or whether it's better to not include the root, okay? And you're going to do this for each of these subtrees. And then your total score in this entire subtree rooted at U is just your score from each of these subtrees. Okay, so these are the two DP equations that we have. Any questions about these? Okay, so so once we have these DP equations, then we can just sort of use our standard way of solving dynamic programs and then solve this. Okay. However, we know that for dynamic programs, you need to solve these subproblems in some specific order, right? Because if you try to solve it in some arbitrary order, you can't just solve these in some arbitrary order. Okay, you need to solve these in specific orders, and the specific order is that when we're trying to compute this value, right, we must have already computed all of these values. Right. Otherwise, you can't get opt-in of U if you don't have these values for its children, for U's children. Okay. So that means that the order that we solve this DP in has to be that if you try to solve for a node U, for node U, okay, you must already have the values, right, for all its children. Okay. All of these must, Let me erase this. Okay, you must have these values for all its children already computed. Okay, so so what kind of order, what kind of ordering of the nodes can achieve this property? Well, a post order can achieve this property. Okay, so if you I thought that it actually said this. Oh yeah. Okay, in post order. Okay, so if you visit the tree in post order. So again, we set what post order is, right? It means that before visiting a node, you visit all its children first. Okay, so if you do that, right, then by the time you need to compute U's value, you've already visited all the children and you already know all their values. And so therefore, it's possible to compute this opt-in of U and opt-out of U. Okay, so therefore, we're going to run this algorithm in post order. Okay. All right, and if you run this algorithm in post order, then basically the complexity for this algorithm is that you just need to basically look at all of the edges in this tree. Okay, that's the amount of time it takes, right? So it's like order E, okay, where E is the number of edges. Okay? But because we're in a tree, then the number of edges is just n minus 1. It's the number of vertices minus 1. Okay, so therefore this is also equal to order of n, where n is the number of nodes. So therefore, you can run this algorithm, so you can find a maximum weight independent set in a tree in linear time. Okay, any questions about this? Okay. All right. Now, before we talk about the next problem, I just want to sort of talk about so the situation we have is interesting over here, okay? Which is that so we're looking at this independent set problem, and for general graphs, this is going to be an NP complete problem. So probably we need to take exponential time to solve this in general graphs. Okay? But as soon as you focus on trees, then you can solve this very efficiently. You can do it in linear time, right? So why is it that this problem becomes so much easier on trees, right? The only difference between the general case, I mean, like in general, it takes exponential time. But once you move to trees, it's much, much easier, right? So there's something special about trees which makes this problem become much easier. Okay, so what is this property of trees? Okay, well, the property of trees is this, okay? So what we're gonna, so suppose you root this tree, okay? Then what you know is that as soon as you root this tree, then you can start talking about these subtrees, right? So for example, suppose U here is the root, okay? Then that breaks the tree into a bunch of subtrees. And what we know about these subtrees is that there are no edges between these subtrees, right? There is no edge between any subtree to another subtree because it's a tree, right? In fact, the only way to get from one subtree to another is through this node U. Okay, so if we don't consider, so suppose you actually take this node U out. Okay, then if you take out this node U, then all of these subtrees become disconnected from each other. And once they become disconnected from each other, then now you can solve the problem on these subtrees independently of each other. Okay, so for example, we're trying to find independent sets. Okay, then once you break these subtrees apart by removing U, then you can find an independent set on the first subtree. Let's call this T1, right? And then you can look for another independent set on T2. And there's no interference between anything that you do in T1 versus anything that you do in T2, right? Because there are no edges between T1 and T2. Okay. Now, if there was an edge between what's this? Right, 1 second here. Now, if there was an edge between T1 and T2, okay. So suppose you have a node over here, and suppose there was an edge between these two subtrees. Okay. Then, if when you're working on T1, if you decide to include this node, okay, then you need to not include this node in T2. Okay, or if you include the node in T2, you need to not include it in T1. Okay. So if there is an edge, then there's interference between T1 and T2. And in that case, you cannot solve T1 and T2 independently from each other, right? You have to solve them sort of together at the same time. But because in a tree, we don't have these edges, then now we can solve T1, T2, and this T3 over here. We can solve them completely independently from each other. Okay. So now we've made this overall problem, we've broken it into many smaller parts. Okay. So we're basically doing divide and conquer on this large problem, right? We can divide it into these smaller parts. Okay. Yeah, well, I mean, actually we're doing dynamic programming, but dynamic programming is just sort of like a fancy version of divide and conquer. Okay. So the point is that when you're working with trees, right, then once you make a decision for this for let's say the root node, okay, then you can work on all of the subtrees independently from each other. Okay. Now these subtrees need to be consistent with this root node, right? So for example, if you do include the root node, okay, then you cannot include the roots of these subtrees, right? So this is what we said over here, right? If you include this root node U over here, right, then you cannot include any of the roots of the subtrees. Okay. However, the subtrees themselves are independent from each other. Okay. Yeah. So this is a basic reason why this problem independent set is solvable on trees. Okay. It's because once you make a decision for the root node, then you can solve the subtrees independently. And in fact, this property where you can decide on the root node and then solve subtrees independently, okay, this holds not only for this independent set problem, but it holds for many other graph problems. Okay, because for many other graph problems, once you break the graph into these into these disconnected components. Okay, then you can solve the problems on each component separately from each other. Okay, many graph problems have this property. So anytime you encounter a problem with this property, that you can solve disconnected subgraphs, you can solve them independently. Okay, then if you as long as you work in trees, okay, you can solve that problem efficiently. Okay, does that make sense what I'm saying? Okay, so so the upshot is that when you focus on trees, you can not only solve independent set efficiently. There are many other vertex cover, dominating set, many other graph problems, coloring. You can solve many of these other problems efficiently as long as you focus on trees. Okay, so and one more thing I'll say about this before we go on to the next problem is that so we see that we can solve the problems efficiently on trees. Okay, but are there other types of graphs where we can also solve these problems efficiently? And it turns out that there's another class of graphs which is more general than trees. Okay, and on this class of graphs, you can typically also solve many graph problems efficiently. Okay, and so this class of graphs is called graphs with bounded tree width. Okay, so I'm not going to define this class of graphs for you because it's a bit complicated. Okay, so if you're interested, you can go look in the algorithm design book by Kleinberg and Tardosh. Okay, and they talk about what these what these graphs are. Okay, but basically, intuitively, these bounded tree width graphs are not trees, but they kind of look like trees. Okay, so what you do, in these bounded tree width graphs, you basically you take a bunch of nodes which are connected to each other, and you form like a big node, like a super node out of these nodes. Okay, so you can take a bunch of these little nodes, you group them together into a super node, right? And then you can take and then you can form a bunch of these groups. Okay, and now the groups actually, the groups look like a tree. Okay, so these super nodes, if you look at the graph in a coarse way, in terms of these super nodes, then the super nodes have the structure of a tree. Okay, so for example, what I'm drawing over here, right? This is kind of like a tree because, we have this branching structure over here. Okay, so that's what these bounded tree width graphs are. It's all the graphs where you can group together these nodes into these super nodes, and then after the grouping, you have a tree structure. Okay, so if you have a graph with bounded tree width, okay, then you can form this grouping on the graph, and then after that, you can apply this dynamic programming idea on these bounded tree width graphs. Okay, because for example, for this bounded tree width graph, right? Once you fix what you're going to do for, let's say, this super node, okay, then this is going to break the entire graph into these disconnected components, and now you can again go solve these disconnected components separately from each other. Okay, yeah. So as long as you can, you have a graph which can be transformed, which can be grouped in this way. Okay, which after the grouping it kind of looks like a tree. Then you can apply this dynamic programming, and then you'll get a fast algorithm. Okay. However, the running time of the algorithm is still going to be exponential in some cases. Okay, because what you need to do is you need to make a decision for this. So just like here, we made a decision about the single node over here. Okay, and there are only two possible decisions whether to include or not include that node. Okay. Well, in the bounded tree width graphs, you need to make a decision for a supernode, right? And a supernode can have multiple nodes in it, and you need to decide how you're going to set all of these nodes. Okay. So therefore, if you have like k nodes in your supernode, then the number of possible settings for these nodes is actually exponential. It's like 2 to the k. Okay, so if you're trying to solve independent set on this problem, right, then you can either choose to include or not include any of these k nodes. So therefore, there are 2 to the k number of choices for that supernode. Okay, and so in that case, your running time is not going to be linear anymore. It'll be something like 2 to the k times some other polynomial in n. Okay, and the 2 to the k comes from the choices that you make for this for each of these supernodes. Okay, yeah, so that's just sort of a high-level description of how these things work. So they're actually a very interesting class of algorithms, and so you again you can take a look at the textbook if you're interested. All right, any questions about independent sets? Okay. All right. So we're not going to take a break today because we already don't have we're already short on time. Okay. So I'm just going to directly jump to the so I probably won't have time to cover this final problem. Okay. But let me just directly jump to the next problem, which is this circular arc covering problem. Okay. So so what's happening over here is that suppose you have a graph. Okay. So this graph is this black thing over here with 4 nodes. Okay. So it's just a ring. Okay. Yeah, so just suppose you have these 4 nodes, okay, 1, 2, 3, 4, okay, and now we're going to make a bunch of edges, okay, so the edges are all these things around the center ring, okay, and these edges are going to cover a consecutive block of these vertices, okay, so for example, this edge E over here, right, this goes from vertex 1 all the way to 4, okay, so it covers these three chunks of the graph, 3 chunks of the center ring, right. All right, so that's E, and then likewise, you know, so A here, right? It only covers this part, okay, the part from 4 to 1, okay, and then B covers from 4 to 1 to 2 to oh well, B goes all the way around, okay, right, and then for example, D over here, D starts at 1, goes to 2, and then stops at 3, okay, yeah. So suppose you have this sort of setup over here. Okay, so you start with these some number of nodes, right? And then you form these edges, and the edges are like a consecutive sequence of these nodes. Okay, and now what we're going to do is we want to give each of these edges. Okay, so the edges are these you know, A, B, C, D, E, F things. Okay, so we want to give each of these edges a color, and the requirement is that if 2 edges overlap with each other, then they have to have different colors. Okay, so for example, this E edge here and the F edge, okay, you see that they overlap in this chunk from 2 to 3 to 4, right? They have an overlap over here. So therefore, we need to color them differently. Okay, so E can be green and then F can be blue. Okay, likewise, this E edge, right? It overlaps with the D edge, right? There's some overlap between these two sectors, right? And so so they need to have different colors. Okay. On the other hand, if you look at edge E and then edge A, okay, you see that there's no overlap, right? A goes from 1 to 4, and then E goes from like you know, I mean, they don't overlap. Okay, and in this case, we can have the same color for A and E. Right? And so now the problem we're trying to solve is that given a graph of this form, we're trying to give the minimum number of colors to all of these edges, right? With the requirement that if 2 edges overlap, you have to give them different colors. Okay. Yeah, and then there's a motivation for this, which is well, I guess I'm not going to talk about this motivation because I don't think I have enough time. Okay, you can read about this motivation up here. Okay, right now it turns out that this problem, so this does not look like a very complicated problem, but this is NP complete. Okay, and so now if you try to solve this problem, then suppose you have M of these edges. Okay, so in this case, we have 6 edges, A through F. Okay, so suppose you have M edges, and suppose you're trying to determine whether you can color all of the edges using only K colors. Okay, now if you do a purely brute force approach, then each of these M edges can have K possible colors. So if you try everything, it's going to be order K to the M. Right. And now the thing is that usually K is pretty small. Okay, so in practice, the way these problems are, when you encounter these problems in practice, K can be a reasonably small, like less than 10, let's say. Okay, but M can be very large. Okay, and so if you have a K to the M time algorithm, this is going to be this is going to be very infeasible. Okay, so for example, if k is like 10 here, if k is like 10 here, right, and then m is like 100, right, then you can't run this algorithm. Okay, this is way too much. So, so instead, what we're going to do is we're going to try to solve this problem. Because it's NP complete, we're not going to try to solve it in purely polynomial time. However, we're going to try to find an algorithm which has this type of running time, where this f of k here, okay, this can be like exponential in k. So for example, it can be something like, 2 to the k. Okay, oops, sorry. I can't write this. Okay, yeah, it can be something like 2 to the k, or even like k to the k. Okay, so we basically don't care what this f is, okay, because k in practice is usually quite small. Okay, right. So we allow exponential running time in terms of k. However, for all of the other parameters, okay, so m here is the number of edges, right? Oops. Right, and then n here is the number of vertices, right? These m and n can be quite large in practice. So therefore, we do not want exponential running time in terms of m and n. Okay, we want a running time which is polynomial in m and n, but possibly exponential in k. Okay, and this way, for most practical instances of the problem, you still get a reasonable running time. Okay, right. So then how do we do this? Well, first of all, before we do this, so this arc coloring problem, okay, this is very similar to another problem that we've already seen, which is interval coloring. Okay, so interval coloring, if you remember, so we talked about this when we talked about greedy algorithms. Okay, so the problem is that you have these intervals, right? A bunch of these intervals over here, and you need to also give the intervals colors in such a way that if two intervals overlap, right, then they cannot have the same color. Okay, so for example, all of these ones over here on the first layer can have color 1. These can have color color 2, and these can have color 3. Okay. Right, now we know that for interval coloring, this problem is actually very easily to solve. You can solve it using a greedy algorithm. Okay, and the reason it was easy to solve was because we had this duality property, which said that the number of colors that you need, okay, the number of colors you need is equal to the depth of the graph. Okay, where the depth means that we look at all points along this graph, right? All points along this graph, and then we find the maximum number of overlapping intervals at any of these points. So in this case, for this graph, the depth is 3. So so then we know that we only need 3 colors to solve this problem. Okay, for interval coloring. Okay. Now for circular arc coloring, it's almost the same problem. Okay, the only difference is that instead of having this interval over here, right, we instead have a circle. Okay, right. So instead of these things lying on the interval, they lie on the circle. So then they can so things can wrap around. Okay, so for example, this I here, right, it can potentially overlap with this B. Okay, now when you're just on the normal interval, this is never going to happen. But if you're doing this on a circle, then then you could have this wraparound issue. And just because you have this wraparound issue, this makes the problem go from linear time solvable, or actually not linear, but anyways, polynomial time solvable to NP complete. Okay, yeah, and the reason is that once you have these wraparound situations, then you no longer have this duality property, the strong duality property. Okay, in fact, you only have weak duality, which is that the number of colors you need is at least equal to your depth. Okay, so as an example of this, so if you look at this graph, okay, then the depth at any point, okay, if you look at any point, you only have 2 overlapping intervals. Okay, but the minimum number of colors you need is actually 3, right? Because, for example, this red interval over here, right, it overlaps at different points with the in different regions. It overlaps with the blue interval and also with the green interval. So therefore, this red thing needs to be different from both red and blue. Okay, so therefore you need 3 colors. Okay, yeah, so this circular arc coloring is different from interval coloring. However, we're still going to try to make use of this basic idea from interval coloring. Okay, because we have such a nice algorithm for that problem. So let's see if we can still use it in some way to help us solve arc coloring. Okay. So the way that we're going to use it is, suppose you have an arc coloring problem. Okay. Then what we're going to do is we're going to choose, let's say, an arbitrary location. Okay, so let's say this V0 here. We're going to add this extra vertex. Okay, and then now you're going to chop all of the intervals at this vertex. And what I mean by chop is that suppose you make a cut over here. Okay, then now we're going to break all of the intervals which overlap at this V0. Okay, we're going to break them into two intervals. So for example, the C thing, right? It overlaps with V0. So we're going to break it into two intervals, and let's call them C prime and then C double prime. Okay, and likewise this B thing, right? It overlaps with V0. And so you're going to break it into two intervals, right? The left part, which we call B prime, right? Or sorry, the right part, right? And then the left part we're going to call B double prime, right? Yeah, and then the same thing for A. Okay, so now once you do that, okay, now suppose you break it at this point, okay? Now imagine that you take this entire circular thing and then you pull it apart like this. Okay, so imagine that you literally grab this thing and you pull. Okay, you pull apart this thing. Okay, then what it's going to become is like this. Okay, because what you're going to have is that this part, this A prime, B prime, C prime, this is going to go over here. Okay, and the other part, A double prime, B double prime, C double prime, this is going to go over here. Right. So once you pull apart this thing, then now you get this situation. And now this situation is just interval coloring now, right? So we've actually somehow transformed circular arc coloring to this interval coloring problem. Okay. However, there's one restriction about this interval coloring. Okay, which is that because what we did was we just made a cut over here. Okay, then what we need is that so in the circular arc coloring problem, the C interval, it only has one color, right? And now after you make the cut, you change C into two intervals, C prime and C double prime, and because they're both equal to C, then that means that C prime and C double prime have to have the same color. Okay, so this C prime here and the C double prime, okay, they have to have the same color. Okay, and likewise this B prime and B double prime, okay, they actually came from the same interval B, and so they also need to have the same color. Okay, and A prime and A double prime need to have the same color. Okay, yeah, so what we did was we transformed circular arc coloring to interval coloring, but it's a special type of interval coloring where if you look at all these intervals at the beginning and at the end, and then you match up the ones that come from the same interval, then these pairs of intervals need to have the same color. Okay, so yeah, so now can we solve this sort of special form of interval coloring? Okay, so now we're going to develop an algorithm to solve this special form of interval coloring. Okay. And again, this is going to use some sort of dynamic programming. So what we're going to do is, so let's just look at this example over here. Okay. So in the beginning, you have three intervals, and we're trying to color them. So you can just color them arbitrarily. Okay. So we have three overlapping intervals, so we need to have three colors. So we'll just give them three arbitrary colors, call them 1, 2, 3. Okay. Right. And now we're going to move. We're just going to move to the right. Okay. And as you move to the right, you see that at this location over here, intervals C prime and A prime end, and we start with intervals E and D. Okay. However, B prime continues through this point. So then what we need to do at this point is we need to give a color to E and D. Okay. And then we need to preserve the same color for B prime. Okay. So that means that B prime, since initially it got color 2, then once you hit this point, it still needs to have color 2. Okay. And then for E and D, right, we just need to give them some kind of different colors. Okay. And so there are actually two possibilities for the colors that E and D get. Right. Either you can make E have color 3 and D 1, right, or you can make E 1 and D 3. Okay. And so that means that at this point, there are two colorings which are compatible with this initial coloring. Right? So we start with this initial arbitrary coloring, and then once you get to this point, there are two compatible colorings. Right? So in order to be compatible, B prime needs to have the same color. Okay, but otherwise we can color E and D arbitrarily. Okay, and so what we're going to do in this algorithm is that we're just going to move from left to right in this interval coloring problem. And anytime you get to a location where some interval ends and maybe some new one starts, okay, then you're going to look at what are all the possible colorings at this location which are compatible with the previous colorings. Okay, so for example, once we get to this location where F starts, okay, then we need to look for compatible colorings. And so let me just erase this. So for example, this coloring, okay, where you have this coloring is compatible with this coloring, right? Because you can color, so F needs to have color 2, okay? If E and D have colors 3 and 1, then F has to have color 2, okay? Or if at this point we chose, if you chose this coloring, okay, then you can have this coloring as a compatible coloring. Right? So this coloring over here becomes is compatible with this coloring, and then this coloring is compatible with that coloring. Okay, right. So what we're doing is at every location we're looking for. So if you have like a bunch of different colorings over here, okay, then at the next location we're looking for all of the colorings which are compatible with any of the colorings here. Okay, any of the colorings in the previous location. Okay. All right, and if you keep going with this, then over here, right, then because F continues through this time point, then we need to have the same color for F, okay? And then E also continues, but D ends and C double prime starts, okay? So therefore, this coloring is compatible with this coloring, and this coloring is compatible with that coloring, okay? And then for the final thing over here, what we have is that, okay, so we have that this color, so over here, okay, we have that this first coloring over here is compatible with either this one, right, or that one, right? And then this coloring is compatible either with this one or that one. Okay, so therefore, at the final location over here, you have 4 colorings which are compatible with this previous coloring. Okay, yeah, so what we do is we go from left to right, and then we find these compatible, or I guess I call it consistent colorings. Okay, and then as you get, and then when you finally get to the end, okay, then we need to check one more thing, which is that initially you started by saying that A, B, and C are going to have colors 1, 2, 3, right? Because A prime actually comes from A. Okay, so that means that A itself has color 1, okay, and B has color 2, C has color 3. And when you get to the end, okay, you have A prime, B prime, and C prime, and these also just correspond to A, B, and C. Okay, and so if initially we have A, B, C having colors 1, 2, 3, then in the end we also have to have A, B, C having colors 1, 2, 3. Okay, so what we're going to do is we're going to look at this final coloring, and we're going to check all of these colorings and see if any of them have A, B, C with colors 1, 2, 3. So for example, for this first one, okay, A, B, C do not have colors 1, 2, 3, right? They have colors 3, 2, 1. Okay, this one also doesn't work. Okay, this one, this one doesn't work. This one doesn't work. This one does work. Okay, this one's okay, right? And then the final one is not okay, right? So what we see is that at the very end, okay, there is one possible coloring which is consistent with the initial coloring. And then furthermore, all of these intermediate colorings were all compatible with each other, right? We can find a chain of compatible colorings. Okay, so the chain is, I'm sorry, this is very messy. Problem is that this pen cannot erase an entire stroke, and I just have to erase this region. Okay, so I'm sorry. Let me just do this. I'm gonna try to do something else with my computer next time. I don't know why it's so slow. Okay. All right, this is still a big mess. Let me try to erase some more. All right, so So let me show you the overall coloring that we're going to use. Okay. So what we have is that this coloring is we're gonna let's work backwards. Okay. So we know that this coloring and this coloring are compatible. Okay. And this coloring is compatible with which one? This is compatible with this one, right? So these two colorings are compatible. Okay. And these two colorings are compatible. And these two colorings are compatible, right? And these two colorings are compatible. Okay, so we have this chain of compatible colorings, right? Plus the compatibility between the very first one and the very last one. Okay, and this chain tells us how we can color all of these intervals, right? We start by coloring A, B, C as 1, 2, 3, right? And then once you have E and D, you color them as 1 and 3, right? And then you color F as 2, and then so on. Okay, right? So we have this chain of compatible colorings. And then overall, this forms a coloring of this interval graph, right? But we know that this interval graph exactly corresponds to the circular arc graph. And so this gives us a coloring of the circular arc graph. Okay, so I'm almost done here. Just give me maybe 1 or 2 more minutes. Okay. Are there any questions about this? Okay, yeah, all right, so then the final thing is I'll just tell you how much, what is the running time for this algorithm. So the running time for this algorithm is that, whenever you go from one coloring to the next coloring, you have to find all the compatible colorings, okay? And so potentially you need to consider all colorings at each location, right? Because maybe, like for example over here, okay, maybe all possible colorings are compatible with the coloring over here. So then how many possible colorings are at this location? Okay. Now, if we only allow ourselves to use k colors, okay, then at each location, there are k factorial possible colorings, right? Because, we have like k of these intervals, right? And each, the first one can have k colors, the next one can have k minus 1 colors, and so on. So at each of these locations, there are k factorial possible colorings. Okay. And then we have to consider the compatibility between all of these colorings. Okay, yeah. So we have to go through all of these nodes, right? So there are n nodes, and at each one of them we have to consider k factorial colorings, right? And so in total, the running time is something like k factorial times n. Okay, and you see that here we got an exponential dependence on the k parameter, but a polynomial dependence on the n parameter. Okay, so if in practice your k is reasonably small, okay, like 10, okay, 10 factorial is something like a few million, okay, so then in that case you have a running time which is somewhat feasible, which is not too bad. Okay, yeah, so I don't have time to go through the final problem. So this is again a vertex cover problem, but in this case we're gonna they focus on a special type of graph. Okay, they're not gonna focus on. So we saw a vertex cover at the very beginning, right? And here what we said is that you allow yourself to have any graph, however you consider only small vertex covers. Okay, and in the last part of this. Okay, is that here you allow yourself to have arbitrarily large covers. However, you only consider special bipartite graphs. Okay, and it turns out that this problem is solvable in polynomial time in bipartite graphs. Okay, yeah. All right. So since our class is shorter than usual, I don't have time to go through this. Okay. If you have questions, you can also ask me. Right. Are there any questions on the first 3 parts? Can you explain why the C at the beginning? On the bottom, well, that's just, yeah, so let's go back to this. All right, I'm gonna try to clean this up if I can. There's a lag of like 5 seconds between me doing something and something actually happening. Right, 1 second here. All right, yeah, so all we did over here was that we took this initial circular graph, okay, and then you split this and pulled it apart and got this linear graph over here, okay, right? And yeah, and then now all you need to do is just color this linear graph, right? And it turns out that this C prime over here corresponds to C double prime over here, and it doesn't matter that we're drawing C prime on top here and C double prime on the bottom. Okay, all this means is that initially, yeah, I mean this doesn't really mean anything. Okay, it's just that the way that it's being drawn, it comes out that way. Okay, but you can see that the coloring, right? So initially you give C a color of 3 over here. Okay, and in the end, if you propagate this all the way through, you're still going to end up with a color of 3 for the C. Okay, and the same thing for A and B. Does that answer your question? Okay, any other questions about anything? Okay, all right, so then that's all I have for today. One other question. So let me just talk about this before we end. Yeah, so if you guys need to leave that's fine, but let me just try to answer this question. Page 11 on the slides, when you add V to S, it seems like V1 and V2 are not added to S because they are leaves. Oh, let's see, page 11. All right. 11 is 11. Oops. 11. So I guess you're talking about page 10, right? Yeah. So what's happening in your picture over here is that no edges contain them. They will not be an S. Oh, okay. So we are going to add. Let's see. Which one did you add? Let me read your thing more carefully. So you added V. And then, so if you add V, okay, so let's just do this on this diagram over here. Yeah, so if you add, let's say, if you add this node, okay, then you're going to take out the U and all the adjacent edges, and eventually you will add this other node, okay? So in your example, later on, I will add V1 and V2. Okay. It's just that because I'm doing this step by step, sequentially, right? I don't add V1, V1, and V2 at the same time. Okay, I add them one by one, but eventually I will add V1 and V2 also. Okay, does that answer your question? Okay, yeah. So again, I am going to add all 3 nodes, V, V1, and V2. Okay, it's just that I don't add them at the same time. Okay, any other questions? Okay, so then hopefully we have a lecture on next Tuesday. And so I don't know what the time for that is going to be. I mean, they might change the time again, so I don't know. But if I find out, I'll let you guys know, of course. Okay, so yeah, so then that's all I have for today. And so hopefully I'll see you guys